So I'll be talking about periodic orbit theory of linear response. So, yes, as you can all see. So you can click it. All right. So we're all familiar with linear response systems. It'll be, you have a system described by some Hamiltonian, and you add some small perturbation, delta H, where this epsilon is very small. This is the equilibrium case. And there's also a non-equilibrium case, and we can look at a more general form of this equation, a dynamical system, to which we apply some small perturbation to the flow, delta Vi, with the same small parameter. And so, in particular, we're going to be looking at the latter class of equations today. But the first question is, who cares about these kind of things? So, one physical example would be this case of protein-ligand binding, which was studied by Ikiguchi et al. And so you see they perturb this Hamiltonian with some small potential for each atom in this large protein molecule, induced by proximity to a smaller ligand molecule. And so from this they can compute the linear order perturbation to the ith atom, its position, using this kind of classical approach to linear response theory, which is based on first order perturbation theory. Go next. And you can see a graphic of what they get. The result is that from the proximity of this ligand molecule, each of these atoms on the protein is going to be displaced some amount. And you see that the result agrees fairly well with the crystallography data. And so another case of physical example would be granular materials. So people have analyzed this linear response of granular materials to study the scaling behavior of different constants near the jamming transition, such as the elastic contacts and the contact numbers. They linearize these forces in terms of a dynamical matrix, and that's another interesting case. But the question that I want to talk about today is, what can periodic orbit theory do for the computation of these variations of observables due to linear perturbations? And so first, just a brief review to lay down some of the terminology. Of course, we have cycle expansions based on this dynamical zeta function. And we can group these into fundamental contributions and curvature corrections. This is nothing new. And the important thing here is that cycle expansions are going to be dominated by the short cycles, as we all know. And so we can also use these to compute certain dynamical averages of observables, using this condition on the zeta function where S of alpha is the alphth eigenvalue of the evolution operator. And so in terms of cycle expansions, we can rewrite it like so using the local traces. And you get an equation of this form where G is a function of this eigenvalue and the parameter beta. And so looking at the first derivative, can compute that. Continue. And you can get the G weighted averages for the mean cycle period and this observable A. And the cycle averaging formula for the expectation value of A. This is all just straight from Chaos Book. And so now looking at what this project will actually be about, linear response. So we can compute, starting with a system of this form, dxi is equal to vi. With this, we can construct this zeta function for it. And then if we apply a small perturbation, the result is that if this is sufficiently small, it will just shift the eigenvalues by some small amount, delta S alpha. And so the new condition on the zeta function, the new perturbed zeta function, will be this. And so now is the part where we make the actual linear approximation. We can expand this condition to linear order. And from that, easily compute the shift of these eigenvalues, which is the quantity that we're interested in. And so in this approximation, we can compute the variation of each eigenvalue just from the perturbed zeta function. And so the cycle expansion of the perturbed zeta function will just be the unperturbed zeta function plus or minus any new or lost cycles, but we're going to assume that the dynamics are structurally stable. So then we can rewrite the cycle expansion in terms of the addition of these little perturbations to each of the traces. And using the local trace formula, we can compute this small perturbation just by expanding in terms of small perturbations to this observable A, this mean cycle period, and the Floquet multipliers. And so now putting everything back together in the linear approximation, we can rewrite this as approximately the zeroth eigenvalue. Again, everything is linear here. From which, as you probably could have guessed, you will get for this derivative, it will just be the negative of the mean cycle period weighted by the zeta function. And plugging everything back in, this is just that little variation of the traces. You can get an expression for this small shift of the eigenvalues. And so now for the kind of base case example that I've worked so far, we can look at the piecewise linear repeller, the tent map. The black is the base case of the tent map with lambda 0 is equal to 4, lambda 1 is 2, and red is a slightly perturbed version. You can see the actual equations of the map there. And I chose this because the evolution operator is a very simple form from which we can get an exact expression for the leading eigenvalue. And so this, the interesting observable that I'm going to look at is the escape rate of this repeller, in particular just the negative of leading eigenvalue there. And so we get the exact value just from that matrix. And we can consider this very simple perturbation to the flow. It's just a linear perturbation parameterized by the different domains. And so that is, we can rewrite this map like so for epsilon bounded from 0 to 1. And so using that expression for the small shift in the eigenvalues I showed before, first we take beta is equal to 0 because we're using uniform measure. And next, these shifts in the cycle periods are going to be 0. And we get this expression for the shift in those eigenvalues in terms of the zeta weighted average of the cycle length and the shift in the Floquet multipliers. And so from that you can just plug in these values. And here I only use the fundamental contributions approximation just to make it easier. And so the question is, how good is this? And so we can plot. Here you see in red is the periodic orbit theory calculation, and black is the exact expression. This is for the shift of the escape rate in terms of increasing epsilon. And so we see that this linear response is good if epsilon is sufficiently small. And also we can do a numerical calculation, which isn't too interesting in this case since we have an exact form for these eigenvalues, but in future tests we would need to do that. So the preliminary analytic work has shown that this periodic orbit theory formulation of linear response can make accurate predictions assuming the perturbing fields are sufficiently weak. And so the next step would be to apply this to something more interesting, which is where I want suggestions. I have no idea where to go next with this. So if anyone can suggest an interesting system to perturb, I would be very grateful for that. And so we can also compare this to some traditional methods for linear response. For example, work has been done with the Lorentz system, various other things. And that's all.
So the time delay systems I've looked at, which are all continuous, so we have poles in our transfer function. So we have discrete eigenvalues in the exact case, but then when we have the time delay, we end up with like a continuum or an infinite number of eigenvalues. And I assume you're seeing this is why you're applying it to a map, I guess, so you can still just get lots of like a manageable set.
Right, something manageable for the first order case, but
yeah. Okay, I assume that's why you're using a discrete case set of continuous.
Right, but the next step would be to look at a continuous case. I think that'll be a lot more interesting. So this map case is really trivial, but it would be interesting.
You have to make it work there before you can apply it.
Exactly. Thanks.
Have you looked at anything where the perturbation breaks the symmetry?
So that's something I thought would be very... so have we looked at anything where the perturbation breaks the symmetry? So that I think would be very interesting. That's part of why I put up the Lorentz system, which has SO2 equivariance, but it might be interesting to choose perturbation that'll break that. That's a very good question. I like that suggestion a lot. Anything else?
All right. Let's thank to Benjamin again, and our next speaker is Michael and his